We have two wonderful speakers from different parts of the world. This is Glenn Leder, who's an emeritus professor of mathematics from the University of Nebraska at Lincoln. And Glenn is author of textbooks in calculus and modeling in biology, and has built a community around COVID modeling and put data forth. So he's going to talk to us about adding a vaccination, which is something we all want and need to do. But I'm not going to preach. I'll let him do that. Mark?
Yeah, not enough of us want to add vaccination to our own personal portfolios. And that will come up in my talk. So with apologies to anyone who comes in late, I'm going to do the take-home message at the beginning. So a lot of people say all models are wrong, but some are useful. And I really hate this quote. Being different from the subject of a painting does not make a painting wrong. Paintings are good or bad, depending on whether they capture the essence of their subject, but they can't be wrong. And similarly, even the worst models are not wrong. The better aphorism is only good models are useful. Modeling is not about turning a narrative into a mathematical structure and then analyzing the structure, although we do these things. Modeling is really about finding an appropriate narrative, which can only be done in hindsight. So as I go through this talk, we'll see some hindsight where we discover that a model that we created is not very good. So let's start with a standard vaccination model. I'm going to add vaccination to the standard SEIR model. Just as a quick note, if you're doing models on an epidemic timescale and looking at short-term behavior, you should never use the SIR model. The extra E class is extremely important in short-term models, so you should always include it. I use some color coding. Blue processes are instantaneous transitions like radioactive decay, and red processes are transmission. So vaccination here is an instantaneous transition that takes people from susceptible to removed. And so for people who aren't really familiar with these diagrams, you turn the diagram into a set of differential equations. I won't include the differential equations most of the time, but once in a while, I'll include them in the talk. So a disclaimer here, the model I'm using is a little too simple for COVID-19. But nevertheless, we'll use parameters that roughly match the situation about a year ago. And since the presentations are going to be posted online, I'm not going to go through all the small details. Some of these we just don't have time for. The graphs for a COVID-19 model would be similar. So I'm going to take that vaccination parameter to be 0.04, which means that the mean time for vaccination is 25 days. That's maybe pretty optimistic. And I'm going to take an effective reproduction number of 4.0 corresponding to the Delta strain with limited mask use and social distancing. My estimate is that the actual basic reproductive number for Delta is about 8. And so these plots show what happens in the model 0 scenario that we're looking at right now. The fraction vaccinated climbs pretty quickly, and we get a significant impact on the scenario. So the scenario involves a new peak because we just started Delta, which has a higher basic reproductive number. So we started out with a relatively low fraction of infectious people, but then it tripled within a couple of weeks when we switched to Delta if there's no vaccine, and it goes up some, but not that bad in model 0. So vaccination looks really effective, but there are things that are wrong with this model. So take about 15 seconds. We don't have a lot of time. So take about 15 seconds to try to jot down one thing that you notice that's wrong with this model. I'm going to write down 4 things, 3 of which we'll address in the talk. Okay, so I'm writing them down not in the order in which I'm going to address them. So the first thing I'm going to address is that in this model, nobody refuses the vaccine. The second thing that I'm going to address is that in this model, distribution is instantaneous. If you go back to the plot of the fraction vaccinated, it goes up really fast. That's not realistic. When you get vaccinated, you have to make an appointment, and it takes about 10 to 15 minutes to get vaccinated. And so the number of people who can be vaccinated depends on how many vaccinators there are. Supply is unlimited in this model. So in reality, it depended not only on how many vaccinators there were, but how many doses there were. And those are two different kinds of limitations, so they have to be treated differently. And lastly, I'm not going to address this in this talk because it involves going beyond the SEIR model, and I don't have much time. But vaccine always confers immunity in this model, which was what I assumed originally, but it's clearly not true for Omicron. My wife can attest to that, as well as many, many other people. Well, and me too. So let's talk about vaccine refusal. This is fairly easy to address. Unfortunately, it doesn't really fix the problem. So to address this, let's partition the susceptible class into a vaccine refuser group and a pre-vaccination group. And so both the P and S groups involve a transmission process that take them to the latent class. And the vaccination process only applies to the pre-vaccinated, not the susceptible who refuse to get vaccinated. So we'll assume the time zero susceptible fraction is S naught. And so a fraction R of these are vaccine refusers, and the remaining fraction, 1 minus R, are people who are in line to get the vaccine. So for the United States average, we'll take R to be 36%. That's based on data I just collected a few days ago. It's only about 10% in Portugal and Chile. So if you want to go on a vacation somewhere where you're less likely to get COVID-19, go to Portugal or Chile, don't go to Alabama. So here's the new picture. And so you can see that the number of people vaccinated is smaller and the impact is somewhat smaller, although still pretty impressive. But there's still things that are wrong with this model. The vaccination rate should not depend on R until the pre-vaccinated people are largely done. In February of 2021, the system was completely taken up by people who wanted to be vaccinated. So whether R was 0 or 0.36 shouldn't make any difference in how many people are vaccinated in the first 20 days. And so that's clearly an error in this model. And it's because this model doesn't take into account that there are a limited number of vaccination slots that you can sign up for. So in order to figure that in, let's do a separate vaccination model that's independent of the disease, and then we'll build it into the disease model. So let's let W be the fraction of people who want to be vaccinated. Finding recipients for a vaccinator is like finding a substrate for a biochemical enzyme. So when I was trying to get an appointment with a vaccinator, I was a substrate and I was searching around for a biochemical enzyme, and that enzyme can only handle so many substrates a day, and so I had trouble getting in. And so this is the Michaelis-Menten model. I put a star on the name Menten. I don't have time to talk about science history, but there's a great story about Menten, who was a woman, Maud Menten. There's a great story about how she came to be involved in biochemical research, and I'd love to tell it sometime when we're just chatting, or you can look her up on the internet. So this is the vaccination model. This is the standard Michaelis-Menten dynamics. I've included an extra factor of K, which makes no mathematical difference, but it allows V to have simpler dimensions. And so here's what the vaccination model looks like. So at the beginning, when there's a lot of people who want to be vaccinated, there's a limit, a hard limit to how many people can be vaccinated per unit time. No matter how many people want to be vaccinated. And as more people get vaccinated, the vaccination rate doesn't change much at first. Only when the number of people who want to be vaccinated gets low enough that they have to go out and look for you, does the vaccination rate really slow down. So you get a linear graph of the number of people who have been vaccinated. I forgot to mention this in my plot before. W naught minus W is the number of people who have been vaccinated. So here's the model with a realistic distribution or distribution for the vaccine. It's the same model as before, except now phi depends on W. And so I need a separate model for W, which I gave you before. So I need to couple that W model in so that I can calculate phi at each time step and use it in the P equation. And we get these results. So I'm assuming the maximum vaccination rate is 1% per day. And that's based on how many people there are to do the vaccinations. How many clinics are there? How quickly can we do the vaccinations? This might be pretty optimistic, but it corresponds to the parameter values I picked in the earlier models. And so slowing the distribution down significantly decreases the impact of the vaccine. We get the purple graph now, which is not that far from the blue one. So that's kind of discouraging, but it's also overly optimistic, because the maximum vaccination rate depends on more than how many people there are operating vaccine clinics. It also depends on how many doses there are, and the number of doses is pretty low at first because they roll out the vaccine before they have fully ramped up production. So a more realistic model would have this V parameter that's 1 over time. That should be, say, a ramped linear function that eventually reaches its maximum value, but not right away. And so the number of people who are vaccinated actually looks more like the green curve than the purple one. And I'm sure if you looked at realistic data, which I could actually get because my son is a data analyst for the University of Colorado Health Center. And so if you actually look at the data, I think what you'll see is that the number of people who are vaccinated followed this ramped function, much more so than it followed the constant one. And now the results are hardly good at all. So the vaccine hardly makes any difference in this scenario. Now, this scenario assumed a quick relaxing of mitigation strategies. Think Florida. That's because I picked an effective basic reproductive number of 4. The effective basic reproductive number of Delta, if you're doing a better job of mitigation, is lower than 4. So what would happen if we were doing New York instead of Florida? Well, so now the top panels are the ones we saw before with an effective basic reproduction number of 4. The bottom panels have an effective reproduction number of 2.5. So on the left, you see the fraction who are vaccinated. So I went over these graphs kind of quick because I wasn't sure I had enough time. I do have enough time to talk about them a little bit more. So on the left, we're repeating the basic information of how many people have been vaccinated. In the middle one, we're looking at the impact on the healthcare system. How many people are infectious at a given time? And so the peak, so with the green one, our new most sophisticated model, it's hardly different with a effective reproduction number of 4. It's hardly different from the model without vaccination. If the effective reproduction number is 2.5, then vaccination makes a much bigger difference. It still doesn't make as much of a difference as we would like. And in fact, that is what happened. The Delta strain took off, and there were lots of peaks in lots of different places, even though we were starting to do vaccination. And even if we'd been able to vaccinate everyone who wanted to be vaccinated, that difference wouldn't have mattered until about May, when we started running out of, when we started having more appointment slots than people who wanted them. Right, so again, back to I should have repeated my first slide with the take-home message. So the take-home message is that modeling is not primarily about writing down a narrative, turning it into a math problem, and doing the math. Modeling is mostly about getting the narrative right. And in order to get the narrative right, you have to critique the assumptions that go into it, and you also have to critique the results that come out of it. I saved myself a little bit of time to show you some resources that you can use in addition to what's in my talk. So here are a couple of resources online. Brian mentioned that I had tried to build, I don't know how effective I was, but I at least built a small community of people who teach COVID modeling in lower level courses. And this is differential equations all the way down to high school algebra. So one of these has a classroom activity and some teaching modules in Excel and MATLAB for the basic SIR model, and another one has the COVID module, which is actually where I started. My colleague Michelle Homp and I wrote a paper that was published in Primus. You can find this online. on using a COVID-19 model in various classroom settings to assess the effects of interventions. So here we looked at the different interventions, and we also looked a lot at the accuracy of public statements made by public officials. The short answer is that virtually everything Anthony Fauci said was correct, and virtually everything politicians said was wrong. Michelle and I also have written a teaching module that's intended to be a guide for research projects for students in community colleges and calculus classes. This has not been published yet. It's in a book that's in press. And the second edition of my mathematical biology book will be out eventually. I'm just finishing up some revisions right now. It's already been reviewed, so it'll still take a while. Hopefully by the end of this year. And I just wanted to briefly give the table of contents so you can see how what I'm teaching now what I'm talking about now fits in with the book. So I have a long chapter on mechanistic modeling. The vaccination model is in the section on transition processes. There's a section on interaction processes, a couple of sections that develop and analyze the SEIR epidemic model, a section that deals with scenarios from the COVID-19 pandemic. And it wasn't relevant for this talk, but I also have a section on how to add demographics to an epidemic model to make an endemic disease model. And then the last three chapters are the basic mathematics of analyzing dynamical systems. Feel free to shoot me an email to receive updates or offer feedback. And I think that's pretty much what time I have. Maybe I've left 1 or 2 minutes for questions.
Yes, we do have time.
Before I do that, I want to just say one thing, because I note that Deb Hughes-Hallett is in the audience. At the very beginning of my career, when I was a very new professor at the University of Nebraska, we adopted the Hughes-Hallett et al. Calculus book. And Deb came out to give us some presentations on how to teach from it. And that was one of the most inspiring weeks that I had as a mathematics professor. And a lot of my teaching of differential equations has built off things that I learned from that week and from the book. Okay, now I'm ready for questions.
That's one of the reasons we invited Deb, so she will hear that from many of us. Thank you, Deb.
Thank you, Glenn. I remember vividly coming to your class and being presented with a lecture hall of students. So it was great.
I'm sure you don't remember me personally. I wasn't teaching
yes,
calculus then.
Oh, yes, I do.
Yep. Glenn is not soft-spoken, so it's easy.
No, as an undergraduate, I tried very hard sometimes to not be the first person whose name the instructor knew, but I was never able to accomplish that, never once.
Okay, are there any technical questions? We have a few minutes. Elena starts at at 6:10. Any questions? You can tell from many of these talks, and this one in particular, the engagement, the social consciousness that mathematicians bring to what they're trying to do. And there are some people that probably believe that's just aggrandizement. They're trying to put stuff to make their mathematics legitimate. If you listen to the talk on cryptology from Craig Bowers, I mean, if we didn't break the German Enigma machine, the war would have gone on for another year. Think about what World War II would have been like for another year. And so mathematicians and the mathematics and the underlying science that goes to this pandemic we're in now is real. And what Glenn brings is that passion that says, you can make sense out of this. You can infer.
I would add to that, though, that when you look at papers that use mathematics in a context, it's important to judge whether they are actually doing modeling.
Yes.
So, for example, I was sent a paper to review that I rejected because it was a math paper in which the introduction said something about COVID-19, but the model had nothing to do with COVID-19,
yes.
and there weren't any there weren't any modeling conclusions. The author didn't do any modeling activities. He merely appended a narrative. So when you're reading a paper that purports to be about a modeling topic, you can tell by reading it whether the author is really doing modeling or not. There should always be some sense of the importance of connecting the narrative to the model and connecting results, if not data, at least qualitative results to realistic observations.
And you certainly got your share of modeling in it, talk about modeling and mathematics. Thank you, Glenn, very much. Okay, we can keep chatting, but Elena wants to, that's our way of saying thank you. Okay.